Good morning, everyone. Thank you very much for selecting and choosing to be here today, this morning. If you've been here in the last couple of days, we spoke about relational databases, how you can run and manage relational databases on AWS, spinning up Linux instances on AWS. Today, we're going to talk about matching databases to your workload. A brief, story about myself. I joined AWS 3 years ago in 2016, and prior to that, I was at Yahoo, managing a lot of engineering and operations. Was a DBA there for about 10, 15 years. That's what my previous life has been. Managed a number of Oracle and MySQL databases. So I have been in the relational database world for a very long time. And when I started looking at how the database world has evolved, that is fascinating. Right, how things have evolved from relational database to where it is today, where you have a number of choices based on what your workload is. And we're going to talk about that in this session here. So the question is, what are we going to talk today? We're going to talk about what is database workload classification, what are the traditional approaches that we have adopted, like in my personal experience, having used relational database for every single problem that comes your way, because that's the only tool we used to have. And how do we scale relational databases? How does NoSQL databases compare to this? And different flavors of NoSQL databases that's available in AWS. So we can go through a few options that you have based on what's the workload and what's the problem you're trying to solve, and what database to choose when. So when you go on, I worked with a lot of developers in my past life, and today I work with a lot of customers. The vertical that I work in is education. So we work with a lot of higher education customers, K through 12 schools, and edtechs or education technology companies that focus on education. And we work with them very closely in the problem of scale that they're solving. So if any of you own an edtech, if you're in a startup that is focusing on education, please come and talk to us. We like to help you. There are a number of programs that we like to fund to get you up and running on AWS. So that's on the side, self-marketing for our group. But when we go and talk to developers, why did you choose a particular database for your workload? The normal answers that you get is, we heard some X is the best thing or the newest thing available in the market. Right? It could be MongoDB, it could be Dynamo, it could be a flavor of Postgres or MySQL. Or we have a site-wide license. In education, we hear that a lot. We have a site-wide license for Oracle or Microsoft SQL, and that's why for every single problem, we'll create an Oracle database and solve the problem using that database. Or, our teams know how to use the database very well. That's a very valid use case. You have the muscle, you have built that muscle to support that particular software or database, and you want to leverage that. But these are typical reasons that we've heard. So why did you choose a database? This database has to be purpose-built to support the application that it's designed to do, right? So we will dig a little bit more into that on how do you go about choosing a particular database for your workload. So what are the different types of database workloads today that we run into constantly? One is OLTP, that's online transactional processing. This could be your ERP systems that you're running, financial, HR systems, where it is highly transactional. Imagine an ERP system where a team is constantly putting in invoices for their customers. That's all they're doing. You exactly know what the workload is. You have a software that's sitting in and putting the invoices. Another team is paying off those invoices to whatever goods were delivered, right? These are traditionally online transactional processing. Then you have analytical processing. You want to do some kind of operational reporting. For example, how many customers have paid or overdue beyond 90 days. These are standard classical reports that you would run in an ERP system, in a data warehouse that's tied to an ERP system. And then you have the decision support system. This is more, you're trying to solve the problem for the business, the long-term problem. So you're going across multiple different types data sources. It could be structured, semi-structured data sources that you're running across reports. These reports can take longer to run. It might take a few seconds to come back, but you're not too focused on latency at that point. If you look at transactional processing, you want to have the fastest time to enter an invoice or make a payment, right? So that is traditionally how OLTP is built. But decision support systems can take a few seconds, but then you want to run that analytical report that solves the problem for your business. This is typically how different types of workloads that we have seen. So sizing the workload. So, you know, on a non-cloud, on an on-prem system, when you're sizing a workload, you make some assumptions on what your system is going to be sized at in a year, 2 years, 3 years from now, and then that's what you size. You buy the biggest box that's available at that time, and then you go through this step function of sizing up your database. So, I mean, I think most of you have seen this sizing on an on-prem systems, where you go through the step function of adding new servers every time you hit a bottleneck. So at any given point, you either have excess capacity or you have customers who are not satisfied, right? Because you are always in the place where you have capacity that you're procuring. It takes 6 to 8 weeks for you to get a server racked and for your database to start using that capacity. So that's where the dissatisfied part of the curve is. And initially, when you sized, you made some assumptions and sized it for the next 3, 4 years, and you have a lot of excess capacities there. In fact, in this graph, there's only one point there, or a couple of points there where your capacity and the user expectation is matched up, right? That's where those lines intersect. That's the only point where you have the exact capacity for your workload. Every time else, you either have an excess capacity or you have customers' performance issues where the customers are dissatisfied. So traditionally, this is how we size databases. We bought a box, and once the database outgrew that box, we bought a bigger box. And then once that outgrew that bigger box, we bought an even bigger box. And finally, we ran out of bigger boxes to host these databases. And then once your database becomes really, really large, you go to strategies where you shard the database. So you split up data into logical pieces, and each of the pieces goes to its own database. And we did that at Yahoo, and we landed up with like a 50-node cluster of databases. Now, how do you manage that cluster? Right? You need a team that manages a cluster, and eventually you lose that battle as well. So that's how relational databases have traditionally been sized and managed. Now, in NoSQL database, we go into the design patterns of NoSQL database in a couple of slides. But traditionally, NoSQL databases have highly de-normalized data, where if you talk about relational databases, we generally talk about normalized data, where you have a lot of reference keys, referential integrities, foreign keys, referencing other tables. In a NoSQL architecture, the data model is highly de-normalized, which means that all the data that you need for a particular transaction all sits in the same row, right? And we'll go into why this design has evolved and become more popular in a couple of slides. But in such a model now, because it is highly de-normalized, and you don't have those referential integrities between tables, you can shard the data in terms of partition keys. You choose a partition key where you can split the data equally across in different pieces. So once your data grows, you just get a new partition key and split it off separately. And if your database becomes even more bigger, then you choose a more finer control partition key, so you have bigger partitions. And there are some compromises in design patterns that you make in this design, and we'll go through that in a minute. So this is exactly what I was trying to explain, where you have these partition keys, and each partition goes to its own server, and now you can have a form of servers that will deal with that bucket of data that belongs to that partition. So when you're choosing a database, there are, let me go through all the pieces that comes in this slide. Okay. So when you're going through selecting a particular database for your workload, there are 3 key fundamental concepts that you want to keep in mind. Any given database will have a capacity, a concurrency, where when you enter data or commit the data into the database, any subsequent read should see or get the value of the latest committed data. That is concurrency. or consistency. All data reads are stored, and any subsequent reads access the data. Right? Availability is if you have a multi-node cluster, if the instance goes down, is your database available for both read and write operations? It should be both read and write. You could have only read-only operation, which means that for that point of time, nobody can write data into the database. So when you're talking about consistency, availability, you're talking about both read and write availability. And then partition tolerance. In your database architecture, in the physical architecture, if any one of your component goes down, how does your database handle that failure? Is it available for your customers to continue their business process, ignoring what that failure happened? Now, databases have to choose between these three key elements. They have to choose two of them, and they have to sacrifice. They have to make a decision on what they're going to sacrifice in these three pillars. So relational databases, which run on a single server, have an availability sorted out, because if the server is down, the entire database is down. If the server is up, it's available for read and write. So availability and consistency are the two pillars that relational databases traditionally pick. So consistency is if you have an Oracle database or a MySQL or Postgres, you enter a record or an invoice, it goes, commits into the database. Any subsequent reads will go and read that data that's committed. And they have algorithms of, Oracle has these redo logs where it will see what's the data in the table, what's the data in the buffer cache, and make sure which is the latest timestamp to pick up the latest record that's currently committed in the database. So that's how relational databases have this mechanism of doing consistency. Now, partition tolerance is something, we have multi-node clusters in MySQL, in Postgres, in Oracle. There are different, the same clustering technology is implemented with slightly different variations, but all of these technologies have a bottleneck where any one of these components goes down, the entire database goes down. It is not tolerant to having failures within that database architecture. Now, if you take a look at NoSQL databases, they have given the pillar that they compromise on is consistency. There is a concept in NoSQL databases called eventual consistency. So when a user goes and commits data into the database, it might take a few milliseconds for that data to propagate to all the nodes which are part of that database. Now, in that millisecond delay, if another person comes and reads the data, there is a chance that the data can be stale. So that is where the consistency compromises. This type of consistency model is called eventual consistency, where data will eventually be propagated to all the nodes which are part of the database, but there might be a few milliseconds of delay. You don't get that delay in relational databases. NoSQL, that's where they made the compromise. And now, if you take out the C pillar of the three pillars there, you talk about A and P, partition tolerance, where you have NoSQL databases that are spread across hundreds of servers. If one of the servers goes down, that's perfectly fine. There will be other nodes that are available for the database to be up. And we'll talk about how DynamoDB handles partition tolerance when we go deeper into DynamoDB. So I've got some of the databases here, which popular databases that's available today, and which particular category they fall into. If you see there, the CA, where there's consistency and availability, you have a lot of the relational databases. You have Microsoft SQL, Oracle, DB2, Postgres, and other relational databases. In the consistency versus partition tolerance, we have DynamoDB, Couchbase, Memcache, Redis, and other key value pair databases. And in the availability and partition tolerance, we have Cassandra. DynamoDB has a couple of modes. We talk about that. They have eventual consistency and strong consistency available. When you create a table, you can choose. So DynamoDB is the only database that falls into both these categories, where you can either choose availability and partition tolerance, or you could choose consistency and partition tolerance. So
DynamoDB, so at any given time, either has to be picked.
Yeah.
in any given time, either it's a consistency or partially, or availability or partially.
Correct. So the question is, as a user, do you have to pick any of these two of the three pillars when you pick DynamoDB? That is right. So when you go and configure a DynamoDB table on the console, you get to choose whether you want strong consistency or eventual consistency. So that is when you're making the choice of which two of the pillars are critical for you. So this is a technology adoption and hype curve. So anytime there is a new technology, there is early adopters. And then there is early adopters go and implement the new technology using the same old concepts that they have learned. This is very true with databases. For the last 30, 40 years, we are so used to relational database models and having a normalized architecture for our application. And normally developers go use a NoSQL database and try to implement the same normalized architecture in a NoSQL database. So what are you doing then? Then you're doing those joins and handling all the concurrence, the joins at the application layer. So you're going to the database, doing a select star, and in the application layer, you're trying to do all the business logic of joins, and then you run into performance issues. So that's where early adopters get into some kind of disappointment in terms of why the technology is not working. So you need to build a new muscle, think through in a different angle when you're starting to use a new technology. Then you have the early majority adopters. And in the last 10 years, I think NoSQL is slightly getting into the early majority concept. I was doing some research in preparing for this session. I think 2007 was when Amazon released the DynamoDB white paper, and a lot of the NoSQL databases have eventually come out of that white paper that was released, I think around 2007, 2008 timeframe. That white paper is publicly available if you want to read about why a NoSQL database was created in Amazon, what was the problems we're trying to solve. That's a very interesting and very dense white paper if you want some. You have an afternoon free and you want to read through that. That might be a good pick. And then you have late majority and laggards. We have gone through big, large enterprises. I go through a lot of higher educational institutions that are using ERP systems that are probably 20, 30 years old. I went to an institute like about 3 months ago. They were still using Solaris. Right? Solaris has been dead for many, many years now. So it takes time depending on what your organization is, where you are in your growth phase, it might take time to adopt technology. So when you are on the AWS platform, what are the different database flavors that you have access to? So I have summarized here. There are a few of these that we went through in the last couple of days, especially RDS, relational database, how to run relational databases. Aurora is a Postgres-compatible database that is managed by Amazon for you. So it can scale, the scaling, managing, backups, recovery, everything is handled by AWS. And you as a consumer just need to start putting data in, and it scales automatically. And I think there was a session in the last couple of days. If you can go to the Git repo and play with that particular workshop. That's the relational database world. In the NoSQL, we have DynamoDB, which we are going to dive a little deep today. And today's workshop is also built on DynamoDB, so you'll get some hands-on experience creating a table and manipulating data within DynamoDB. Neptune is a graph database. We announced that in reInvent this year. This is a popular design pattern for social media companies like Facebook or LinkedIn, where you want to have link friends of friends of friends, and what their interests are. If you try to implement that, we'll go into that in a couple of slides. Elasticache is a caching mechanism where it's typically Redis and Memcached are the open source databases for cache. So if you have a relational database where your application server is hitting the database for every single select, you're going to have a performance degradation there because relational databases are traditionally slow. So one strategy would be to, if the query is hit multiple times, you cache it in a very fast in-memory database like Redis or Memcache, and then your query no longer hits the database. It gets the data from the in-memory cache, and it makes it much more faster. QLDB is a ledger database, a quantum ledger database that we announced in reInvent last year. I think it is still in preview, but it is based on open source concepts of blockchain. I think Ethereum and some of those are ledger or concepts on which the ledger database is built, so that it is a zero trust system. If you have a financial system or a supply chain, you don't want to trust a person or a system, so you have a mechanism where multiple systems are keeping each other in checks and balance. Similar concept as blockchain. That's what the QLDB server database is. We have time stream. There are a number of use cases where you have time series data. It could be the log data in your application server, or it could be IoT systems that are constantly streaming data into your into your system, and it's immutable. You don't go and edit or modify this data. It is data that is sent by your device as a source of truth. You are accumulating the data and running analytics and reports on that data. So that time stream makes it much faster compared to any other database solution you have today. On the analytics side, we spoke about decision support systems. We have Amazon Redshift, which is a columnar database. We'll talk about that later on. What is a columnar database? It is Postgres. It's built on Postgres. It's not Postgres compatible, but that some fork of Postgres was taken and Redshift was built on that. It is a relational database, so you can run relational SQL type queries on Redshift. Elastic MapReduce, EMR. Basically, this is the Hadoop ecosystem that you can run, managed by AWS. Athena is a data lake concept where you can run SQL-like queries on structured, semi-structured data without going through the process of doing an ETL. Right? Traditional data warehouses, if you run it in your system, you have a source of truth, which is your OLTP system, which is highly normalized, and you can't run large queries against that because it's going to bring that system down. So you transport the data, it's called an ETL in traditional world. You extract data, transform it, and load it back into another database so that it is a semi-denormalized. Traditional strategies are like a star schema where you have a huge fact table and you have dimensions around that, and you could run large queries against these systems. You don't have to go through that ETL process. You can run that query at the source when you have engines like Athena. Elasticsearch, this is a search engine that you can pipe your data into that gives you much faster access. Search is designed slightly differently than databases. You have these inverted indexes that are built on all the documents and content that you send, so that your search words are indexed so that it gets to the content much faster when you're doing the search. Kinesis is a connector that you can leverage to stream data into your data warehouse. So you have an IoT system where you have millions of devices streaming data that you want to accumulate in a database. You could stream that data into the database in real time. And Kinesis has a few flavors like Kinesis Streams, Firehose. These are some of the, we had a problem of billions of events happening simultaneously, and those all need to be accumulated and inserted into a database. Now, if you try to do, if each of the devices try to insert data into the database, your database is going to be the biggest bottleneck. So Kinesis allows you to stream it into a pipe which decouples your devices in the edge and your database. So the devices put it into a stream and they forget about it, and the stream eventually takes it and loads it into the database. We'll talk about data lake in one of the later slides, how you can build this data lake and what is the why this is becoming the new normal in terms of data analytics. RDS, I don't want to spend too much time on this slide. We spoke about it last couple of days. You can run any of these flavors of database. On AWS, you don't have to take that overhead of managing the servers, managing backups, patching. These are some of the activities, what we call as undifferentiated activity for a business, right? If you're running a business of a social media software, your strength is not managing databases or servers in the backend. So you want to offload that to a platform that does it for you, and you can leverage all your resources on building your application, or what's the main or, using all your resources for your main application. So DynamoDB, now diving slightly deeper and focusing on DynamoDB, it's a highly scalable petabyte size database. It's fast, consistent performance. The disks under DynamoDB, the way it is designed in the back, it uses SSD disks. And if you're familiar with AWS infrastructure, we have a concept called regions and availability zones. So you have a region, which is a geographic location, which could be US East 1, US West, which is in Oregon, or in California. There are about 5 regions in the United States. And within each region, we have availability zones, which are a minimum distance apart. And each availability zone is a cluster of data centers. So we want to build that redundancy and scalability in the back end for your applications. So when you launch an application and you have 2 web servers for that application, you can choose each of those web servers to be in 2 different availability zones. So if an availability zone goes down because of a natural disaster or because of a power outage or an internet problem, your second availability zone has a completely different set of providers. So we don't have anything common between the availability zones. There is no dependency or a common factor. So if an availability zone goes down, the second availability zone is up and running for you. So your application will continue to work because you have a web server in the second AZ. So I gave that background because the way we have designed DynamoDB is it's a 3 availability zone architecture. So anytime you insert a data into DynamoDB, it makes multiple copies of that across 3 availability zones. So it's a highly available database and highly scalable in the back end. We build DynamoDB is one of the most critical services when we launch a new region in AWS. It's called a tier 1 service. So a region cannot be launched without DynamoDB functioning in that region. So it's a very critical service both for Amazon and for all of our customers. If you take your smartphone and go through your app list, most of those apps are using DynamoDB in the back end. So it is a very prevalent NoSQL database today, and that's why it's built in that architecture. It's fully managed, which means as a user of DynamoDB, the only thing you're worried about is the APIs. So there's a REST API. Even though we have multiple database flavors, you don't have to go through learning each of those architectures. All of them have a REST API as the front end. So as a developer, you just call the REST API to get, put, post, the standard REST API calls. And it's fully managed in the back end in terms of backups. We'll go through that. We have DynamoDB as streams. We'll talk about that in a couple of slides. So the activity of managing, patching, backing up the database is done by Amazon for you. And especially with the architecture that I just spoke about, the 3AZ architecture gives that flexibility. And business critical reliability, we spoke about multi-AZ architectures. So when you start using DynamoDB, how does that organize data as you start inserting records? So we spoke about NoSQL databases having highly de-normalized architecture. So every single row here is called an item. An item is equivalent to a row in a relational database, and attribute is equal to a column in a relational database. But a relational database is very strict in terms of the number of columns. You need to decide that ahead of time, and then every record that you put in has most of the column values. And in DynamoDB, you don't need to have all attributes for every column that you put. So say you are creating a database for the users of your app on your mobile phone. So some users share a lot of their interests, so you could have those as attributes, like what is the favorite sport, what is the favorite movie, whatever interests are there for that user. But some of them might decide not to share that information with you, right? So they might not provide all the attributes. So you can have a highly flexible structure for your items and in a DynamoDB. For the schema, what is critical is the partition key. So every item in the database should have a partition key, and I will go into that shortly. And then you can optionally have a sort key. So a partition key, we spoke about how NoSQL databases are organized. You have these shards based on partition key. They go to a specific bucket, and that's where those records reside. So when you decide what a partition key is, what DynamoDB does a hash of that partition key, and then decides which partition does this data go and sit in. All right, that's why partition key is critical for every item that you insert into DynamoDB. Now, obviously you want to run queries on these items that you inserted into DynamoDB. And that's where the sort key comes into picture. It sorts based on date or time, and you can have a complex sort key so that you could use that in your where clause. You can say select star from this particular table where all orders are less than 30 days, and the sort key index will be used by your query to give that faster. Now, DynamoDB gives you a little bit more flexibility in terms of what's called global secondary indexes and local secondary indexes. So let's go, let me see if that's. This is the side-by-side pattern on the architecture of NoSQL versus SQL databases. If you see what's on my right there is a highly normalized architecture for a relational database. Right? You have about 3, 6, 7 tables for that product feature, and every time you run a query on the product, you need to go and do the joins with 6 other tables to get all that information about that particular product. Who are the actors? This is about movies. What are the albums, books, everything for that particular product. Now, in a NoSQL database, it would be a single table like that, which has all those attributes in a single table. So the query that you run on a NoSQL database is just select star from that table, and you don't have to worry about any joins. Now, if you think why relational databases were designed like that, 30, 40 years ago, storage was very expensive, right? And you had to optimize your architecture to minimize the use of storage. And that's why the repetition of data, in a normalized architecture, what you are achieving is reducing the repetition of the value. You're using an ID instead of the whole value, so you're reducing the amount of space that particular value take by referencing it as an ID, and the value of that ID is stored in let's say it's a state ID. You're storing all the 50 states, and you have a state ID and name of the full state. So any other table that requires that state information will not have to store the name of the full state. It just has to store the ID, and you're saving that much space. But you roll forward 30, 40 years. Today, storage is not expensive, right? What is expensive is compute. So you allowed the CPU to do all those joins and bring the data out in the past. Today, you don't care about duplicating the data, right? If you look at the attribute, the type, price, description, title for every product is going to be stored for every single record. But storage is not expensive. What is expensive is compute, and you want that results to come out really fast. And that's where the design compromises are. Why relational database was designed the way it was designed in the 70s and the 80s, and why NoSQL, why it didn't solve today's problems. So that, let me see if I missed something. So we spoke about the difference between NoSQL and relational databases. I briefly mentioned about local indexes and global indexes. Let me spend a couple of minutes on that. So when you design a table, you design what's the primary key and what's the sort key. And let's say 3 months from now or later on, your requirements changed, your query patterns changed. Now you want a different partition key and a different way to query the index. You could DynamoDB gives you the option of creating what's called the global secondary index. This is a way where you can reorganize the table for handling specific type of queries. Now, the fundamental difference is in NoSQL databases, when you design the table, you want to know exactly what the query patterns are. It's very hard to change the design once you put the architecture in place if your query pattern changes. In a relational database, you can go build an index, and if a query pattern changes, you can look at the explain plan and see how the optimizer decided to run that query and start manipulating the indexes. NoSQL databases, none of the NoSQL database gives you that flexibility. So you want to know how to handle what are the incoming query patterns and design the table based on the query patterns. DynamoDB gives you a little bit more flexibility there. You can build what's called global secondary indexes and change the partition key and sort key. In the local indexes, the index is within a partition. So the global indexes can go across all partitions, and you can change the partition key and sort key. A local indexes operate within a single partition. If you remember the architecture we had for NoSQL databases, where you have partition of data based on the partition key. So you can create about 25 local indexes and about 5 global indexes. So there are some limitations that you need to consider when you start designing the tables. We'll go through that. I think the workshop handles a little bit of that, but you'll see that once you create the table, DynamoDB table. Amazon Neptune is the graph database that we launched at re:Invent. The session after this afternoon is about graph databases in Neptune, so I will go through this faster because we'll have a deeper dive this afternoon. So, sure. Yeah, so the question is, DynamoDB handles inserts and read operations in a highly scalable way. How does DynamoDB handle updates, right? So when two processes are trying to update the same record, how does it handle concurrency? That's a very good question. Timestamp is by default, at the lowermost level, we look at what's the timestamp when the insert happened and take the insert that came in at the latest timestamp. That is how concurrency is. If you look at DynamoDB, we launched a new feature in re:Invent this year called global tables. Today, you can have a DynamoDB table that can span across multiple regions across the world, right? Before that feature, your DynamoDB table would be in a single region across multiple availability zones. The global table gives you the possibility to have multiple DynamoDB table across multiple regions, where it gives you this scenario of having multi-masters, right, where you have inserts from multiple masters. And timestamp is the way where we decide what is the latest update that came in, and then based on the concurrency model that you choose, whether it is strong consistency or eventual consistency, we decide what the next read operation will get. Right? Does that answer your question?
Sort of, but one that, like usually if you look at other databases, it's always last reference or it overwrites the previous page.
Correct.
Right? So if in an inventory model, how much items are left or how many tickets are left to be sold, if you keep reducing,
Correct. Correct. So your question is, if you use a NoSQL database for an OLTP-like application, right, which might be the fundamental topic of today is choosing the right database for your workload. For something like that, I would choose a relational database if you have to be strongly consistent. But DynamoDB introduced these features where you have now transactional concurrency, right? We offer transactional concurrency, which gets very close to, you get the scale and the scalability of DynamoDB with the concurrency that you need for a transaction. And the way DynamoDB decides with multiple masters is based on timestamp. The last write is what finally gets committed. In a global, uh-huh. Current, yeah, correct. Yeah.
Fundamentally, DynamoDB same as H-based like architecture.
So the question is, fundamentally, is DynamoDB like an edge base? So if you look at NoSQL databases, there are about 3 different architectures that are predominantly in the market. One is a key value pair, and key value pair is like a Redis or a memcache, where you have a key and the value is a blob, and you can't manipulate anything within the value. So the way database queries use Redis or memcache, which is key value pair, is if you run a query which says select star from employee tables where employee name is John, it will have a query ID attached to it. And once that query is served, it caches that result in memcache with a value that says the query ID. So next time an exact same query comes with the same query ID, it will fetch the data from the memory instead of going to the database. Now, that's why in relational database, we always tell the developers to use variables and not hard code values in your where clauses, so that each, select star from employee where employee name is John can be a different query ID to where employee name is Cindy, right? But if you use a variable, then it will reuse, the optimizer will reuse the same compiled query. The second one, what DynamoDB is, to answer your question, is called a wide column. Right? A wide column NoSQL databases extends the concept of key value pair. In a key value, like I said, the column, the value is a blob. There is no manipulation that you can do in terms of where clause in the value itself, right? In a wide column, it further splits that key value into further key value pairs. So you can now do where clauses on the value itself, not just on the key. So it can be just a select star from the table where the key is a key value. In DynamoDB, it extends that concept and makes it a wide column where it further divides that value into further key value pairs. Third type of NoSQL is a document database, right? MongoDB is a document database. It stores the value in a JSON format, and you can retrieve the whole document from that database. So DynamoDB is more like Cassandra. I think they are on the same concept designs in terms of how the NoSQL patterns are designed. Amazon Neptune, we spoke about graph. Now, what is the problem that graph database is trying to solve? It is this relation, right? If there's a person, Bill is visiting Paris, he wants to visit Eiffel Tower, and he also wants to see what his friends have seen in Paris. What are the things that they have done? Now, if you put this model in a relational database, it will be something like this, where you have like 8 different tables with names, relationship, places, things, dates, and you're going to run at least 5 different joins to get that information. If you implement this in a de-normalized architecture, you'd still be more complex, but it might be easier. We have Bob, all his relationship, and Bob in graph database is called a node. A node is the key entity there. So in this case, a node is names of all the people here and the main entities, like what can be done, what are the visiting places that you can visit in Paris, and what is Bob's relationship to each of these nodes, right? Bob is a person, he was born on this day, he's a friend of Alice, and his interest is Mona Lisa. So those relationships are all stored in a single record so that you don't have to go to multiple tables to join. But it still makes it more complex if you want to tell Bob everything that he can do when he visits in Paris. And relational database, graph database solves this problem, and we'll go deeper into Neptune in the next section on how this solves this kind of traversing across multiple nodes. Redshift, we spoke about Redshift a couple of minutes ago. It is a highly scalable data warehouse application, data warehouse that. So the way Redshift is organized, spoke about columnar databases. Redshift is a fork of Postgres, and it's a columnar database. In a transactional database, if you insert a record, and the record has 4 columns to it, it goes and inserts that record into a data block, right? And every time you do a select, it reads that whole data block. And sometimes your queries are just querying 1 or 2 columns in a record that has like 50 columns. So Redshift is a column. In a traditional database, the whole row gets inserted into a record. And if you are selecting just 1 or 2 columns for your query, the way the optimizer is going to work is go and read that whole block into the memory, which means 80% of the columns that you read into the memory is not going to be used by your query. The way columnar database stores is it takes all the records of a single column, which typically are similar type of data. It could be names of people or state that they belong to, or date of birth. So it is similar looking data that all are stored together on a single block. So internally, what Redshift does is every time you insert a record, it stores it by selecting all the columns into a single block instead of rows. The advantage with this is it can achieve a very high level of compression. So when you're reading a record into the memory, you can do just a single I/O to get hundreds or thousands of records into the memory. And secondly, the block size is another key differentiator for the Redshift in terms of performance. Traditional databases use like an 8K or 32K block size. Redshift uses 1 meg in block size. So every single I/O, Redshift is reading 1 meg of data from the disk into the memory, right? So it gives you a very high level of performance and reading data from the cache instead of doing multiple I/Os to get that data. It's highly scalable. In real time, you can go and add nodes to the Redshift cluster, where it can, the way Redshift stores is you choose how many nodes you want in a database, and a master node and a slave nodes get allocated. The architecture is there's a master node that has the optimizer and the compiler, and the slave nodes is where all the data sits. So if you run a query like select star from an employee table, the optimizer decides what is the query execution plan that it needs to go and extract data. And it creates that plan and sends that plan down to each of the nodes. So now the nodes don't have to spend that time in the optimizer deciding how the query needs to be executed. All that nodes do is execute whatever query they get from the master node and send the data back to the master node. And the master node compiles, sets the data and pushes it to the user, whichever UI tool that you use. It could be a SQL developer tool or it's a JDBC front end for Redshift, so you could use any tool that supports JDBC, and it will present you in the presentation layer. So that is the scalable. You can, it's inexpensive. You can choose what's the type of hard disk you want. You could choose a magnetic disk. You could choose SSDs. And if you based on your workload, based on the performance that you're expecting, you can decide what is the amount you want to spend. So it could be as less as $1,000 per terabyte of data per year. You could create your data warehouse based on what your requirement is. It's highly secure. Security is key for Amazon, AWS. It is almost job zero for us. So if we see any security challenges, we drop everything else to focus on security. Data encryption at rest and transit. You use HTTPS and data encryption at rest to encrypt all data. You can create your Redshift in a VPC. For folks who are not familiar with or new to AWS. VPC stands for Virtual Private Cloud. So the first thing you do when you launch your workload in AWS is create your own virtual space on the cloud, and then you own that space. You decide who gets in, who gets out, what kind of traffic gets in and gets out. So that makes it very secure, so that you can launch a Redshift database inside your virtual cloud. And we spoke about data encryption at rest. You could bring your own encryption key, right? Say you don't trust anyone, and it's a highly sensitive data, and you don't want anyone to access. So you can bring your own encryption key and encrypt your data using your own encryption key, which means even if somebody gets access to the data, it's just a blob, right? Unless you have that key to decrypt it. Amazon Athena. So Athena is based on Presto. Presto is an open source SQL-like query that you can run on structured, non-structured, semi-structured data. So, and the reason why we call it serverless is you could store all your data. Let's say you have incoming log files or IoT devices streaming data, and you store that on S3. S3 is a very cheap storage. It's about less than 2 cents a gig per month. It's highly durable. It has 11 nines of durability. The reason why we can promise 11 nines of durability is it's a 3AZ architecture, like I told about DynamoDB. Every time you copy data into S3, it makes multiple copies of it across multiple availability zones. So we have the 11 nines of durability, and you have 99.99% availability, right? So that's why S3 is highly durable and extremely cheap to store data. Now, you don't want to move the data into a database just because you want to query the data, right? You want to run queries against the data when it is sitting on S3. So Athena gives you that flexibility to run SQL queries on the data that is sitting without any transformation. Let's say you're getting a CSV file or a JSON file from from your devices or your application files. Typical use cases I've seen is event logs, right? You have an application. Each time a user clicks on some part of your app, you want to track what was the user behavior there, right? Why did the user click? Or how many users clicked on a specific part of your application? These are event logs. And you want to stream those events into S3 and store it there forever. But you can run now SQL queries on that event to say how many people, what was the user behavior, and make changes to your applications based on user behavior. Right? That's the use case where I have seen Athena being very, very popular in adoption. Sorry, what's your question? Correct. So the question was, can you query the content of the document that is stored in S3? That's right. Athena supports certain data formats. You can have data that's coming in CSV files, it's coming in JSON files, or Parquet. There are a lot of different standard formats. So as long as your data is in that format, you can query the data in S3. Oh, sorry, question? So Hadoop, the question is it similar to Hadoop Hive, right? The Hadoop paradigm is slightly different from Athena. Hadoop is very well suited for data processing, right? If you have very large amount of data that you need to be processed to a different format or store it in a different way, Hadoop is really good solution for that. It doesn't give you real-time queries, right? Athena is more for real-time querying without going through the transformation. You want to look at query data in real time as soon as it lands in S3. Simple use cases, right, where we have a lot of customers. They get bank statements or documents from banks or their partners, other SaaS applications they're using. They all typically send it by FTP, and it lands on an S3 bucket. What do you do with that data? Right? Now you can run queries directly against the data without doing any transformation. You don't have to pick. Traditionally, it lands in an FTP server. There's a cron job that goes at night, picks up that file, loads into a database, and now you're running queries. You avoid all that overhead here. Sorry. So it is serverless. It sits on S3. You don't have to manage the storage for S3. It's infinitely expandable. You can store billions and billions of transactions there. You don't have to worry about the overhead of managing S3. That's why it's serverless. There is no infrastructure that you need to worry about. The only thing you're worried about is the JDBC connection or the API to query these. Sorry.
Can you do, like, do you have to index for word querying, or can you query text?
So the question was, do you have to index or can you just query text? Yeah, you can query text. As long as your document is stored in one of those standard formats. All banks, all intercompany transactions happen in a standard format. Either they send it to you in a CSV file, which comes out of an Excel, or it is provided in a JSON format. As long as it is in that format, you can query the text directly.
So Athena is an engine, right, which basically converts the content of S3 into SQL relational database, right? Presents to the
So let me answer it this way. The question was, is Athena an engine that converts data in S3 into a relational database? It doesn't do any conversion. It is an engine which is like an optimizer that allows you, that gives you a SQL-like interface to directly hit the data. There is no conversion in storing data in the intermediate. So I got alert that I have 5 more minutes. I want to complete this rest of the deck here. QLDB, ledger database, we spoke about that. It is zero trust database that we can, it's in preview, and I think you can go and sign up for that and play with it. It is highly useful in financial, supply chain kind of systems where you want all the systems working together to validate and build the trust between the systems. Zero trust is you don't depend on an entity to do the trust. You want a system to be self-sufficient. For example, let us say you have a database, specifically in QLDB. If there's a record inside the database, and traditionally you have a relational database and an application. Application is pretty strong. It can go and validate every change that happened to the record. Now, suppose a developer went to the database directly and updated the data or deleted the data. After that delete is done, you have no track record or no trail of who changed it, what was changed. In the zero trust, you have a signature attached to the change, right? Suppose every time you make a change to the data, the signature gets updated. Now, if somebody a rogue player or a bad actor goes and manipulates the data, the signature cannot be manipulated. So now you know there's a mismatch between the signature and the data that's sitting in the table. So that's where the zero trust comes. You're not trusting any single entity. The system by itself makes sure that the data is immutable and trackable. It'll be prevented. Yeah. So in the query ledger database, it prevents you from manipulating, or it's immutable data. Once you insert the record, it's not changeable. Time series, we spoke about this. Time stream is a database that allows you to put time series data from IoT devices or application log files, and we see a lot of those use cases. So different categories of databases. We have SQL, NoSQL, and graph database. We spoke about SQL. This is pretty standard. We've been using it for the last 30, 40 years. In a NoSQL, the big differentiators are it's scalable horizontally. It's built for OLTP or DSS at scale. It's a highly de-normalized architecture, whereas SQL is normalized. We spoke about what is wide column and what is key value pair in databases. These are the 3 NoSQL that's popular. And so this is when you choose a database, there are 3 things that, 2 of the 3 things that you need to choose: scalability, efficiency, and pattern flexibility, right? These are the 3 pillars. Like we spoke about 3 pillars in terms of SQL versus NoSQL. When you choose a database, choose which of the 2 that's critical for you. If you want pattern flexibility, that you don't know what's the queries that's going to hit the database, and you want to be flexible there, then a relational database can be your an Amazon RDS or an Aurora serverless database might be your right choice. If you want efficiency, database will deliver required query latency for the workload at all times, or you want infinite scale, if you choose between these two, Amazon DynamoDB might be your right choice, right? It gives you eventual consistency, and it allows you for infinite scale. If you want pattern flexibility and infinite scale, which is the sweet spot of a relational database versus infinite scale, then Redshift and Athena might be your right choice. So based on what you want, what are the two of the three things you need, you can choose what is the right AWS service for your workload. You can bring your own database and run it on an EC2 instance, but you're taking the undifferentiated heavy lifting, like backing up, patching, security vulnerabilities. What we are providing here is how do you manage that workload without that undifferentiated heavy lifting that you have to do. So thousands of customers are using DynamoDB today. We spoke about most of the apps on your mobile phone today is using DynamoDB in the backend. And many more are using RDS. Relational databases have been here for 30, 40 years. They're going to be here for a long time. And so we support all the relational database flavors. And there are thousands of customers that are using it. So purpose-built databases. Choose what your infrastructure requirement is and what software, what is the managing that you need to do for the database, right? In terms of infrastructure, capacity planning, provisioning, monitoring, operating system patching, hardware upgrades, and these are the things that AWS takes care for you, and you need to worry about the application. In terms of software, database upgrades, security patches, scaling, monitoring, performance tuning, these are the tools that we provide for each of these database engines that you can very easily look at that information through services and act on that rather than trying to build these services in your applications. So finally, thank you. Thank you for coming today.